All right, strap in everyone, because today we're going deep into the world of data deduplication.
Ooh, yeah, one of my favorites.
And to guide us, we've got this paper called Avoiding the Disk Bottleneck in the Data Domain Deduplication File System.
Catchy.
Yeah, rolls right off the tongue.
But titles aside, this paper's a gem. Really lays out how to make deduplication systems, especially for backups, crazy fast. Even though it's a bit older, the core concepts are still so relevant today.
Absolutely. So whether you're prepping for like a big meeting on data storage, just curious about how deduplication actually works under the hood, or you're just a tech enthusiast who loves a good deep dive, this one's for you.
Couldn't have said it better myself.
Now, let's set the stage a bit. Data backups, we all need them, but man, they can be a real pain, eating up tons of space and taking forever.
Yeah, tell me about it. Remember those old tape backups? Ugh, talk about slow and unreliable. I mean, have you ever actually tried to find something on one of those?
Like searching for a needle in a haystack, right?
More like searching for a specific grain of sand on a beach. And even if you find the right tape, who knows if it's even readable anymore?
So many potential points of failure, it's enough to make you pull your hair out.
Right, and that's where disk-based deduplication comes in, like a knight in shining armor. It cuts out the redundant data, saving you space, and can be way faster than those ancient tape systems.
Okay, so deduplication sounds amazing, but I'm guessing there's a catch.
Well, there's always a catch. The real trick is figuring out how to identify and remove those duplicate chunks of data super fast and without needing a ton of expensive RAM to do it.
Yeah, because RAM can get pricey, especially when you're dealing with huge data sets.
Exactly. Imagine trying to find matching puzzle pieces scattered across a giant warehouse floor. It's a logistical nightmare.
Okay, so that's the challenge. How does this paper and DDFS tackle that problem?
Well, think of DDFS, the Data Domain File System, as our super organized puzzle solver. It takes all those data pieces, breaks them down into variable length segments.
Variable length, huh? Why not just make them all the same size? Wouldn't that be simpler?
You'd think so, right? But think about backup data. It's constantly changing. Even a small edit to a document can create a ripple effect.
Ah, so fixed length segments would get messed up by even tiny changes.
Yep. Variable length segments are way more flexible and can still find those redundant parts, even with all the changes happening. It's kind of like having adjustable shelves in your bookcase to accommodate books of different sizes.
That's a great analogy. Okay, so we've got our data neatly organized into variable length segments. What happens next?
Well, that's where the real magic happens. DDFS creates a unique fingerprint for each segment, like a digital signature.
So kind of like giving each puzzle piece a unique ID number.
Precisely. That way, it can quickly tell if it's already got a copy of that segment stored somewhere else. No need to keep multiple copies of the same thing.
That's super smart. So DDFS is already sounding pretty clever, but I know there's more to it. The paper talks about 3 specific techniques that really make it fly. What's the first one?
The first one is called a summary vector. It's basically a super fast pre-check to see if a segment is likely new. Imagine you've got a giant keyring with thousands of keys.
Okay, I'm picturing it. Lots and lots of keys.
The summary vector is like a special tool that can quickly tell you if a specific key might be on that ring without having to check each key individually.
So it's all about avoiding unnecessary searches.
You got it. And that saves a ton of time when you're dealing with massive amounts of data.
Okay, that's one down. What's the next trick up DDFS's sleeve?
Next up is Stream-Informed Segment Layout, or SISL for short. This one's all about organization. Think about trying to find a specific photo in a jumbled shoebox versus a neatly organized album.
Okay, yeah, that makes a huge difference.
Exactly. SISL keeps related segments together, making finding and retrieving them much faster.
So instead of searching through that entire shoebox, you just flip to the right page in the photo album.
You got it. It streamlines the whole process.
Yeah.
And this leads us to the third technique.
Which is, drum roll please.
Locality preserved caching. This one builds on SISL by taking advantage of a simple fact. When you access one piece of data, you're likely going to need other data nearby pretty soon after. Like when you read a book, you usually read chapters in order.
Oh, so it's like DDFS is anticipating what you'll need next and keeping it handy, like preloading the next chapter in your ebook.
Precisely. This minimizes those pesky disk accesses even further, leading to even faster backup and restore times.
Okay, these 3 techniques sound like they'd make a huge difference, but what about in the real world? Did DDFS actually live up to the hype? Did it pass the performance test?
Oh, it passed with flying colors. We're talking a 99% reduction in disk access, which is mind-blowing.
Wow, 99%. That's almost like eliminating disk access entirely.
It's pretty close, and that means backups could be completed up to 100 times faster than with traditional methods. But what's even more exciting is that these techniques aren't just limited to DDFS.
Oh, tell me more.
They have the potential to revolutionize other areas where finding duplicates quickly is essential.
Okay, now I'm really intrigued. But first, let's take a breath and let everyone absorb all this amazing information about DDFS and its speed secrets.
Welcome back, everyone. Before we jump into those other applications, I think it's important to talk about another major trend that's happening in the world of computing multi-core processors.
Multi-core processors, those CPUs with not just 2 or 4 cores, but sometimes dozens or even hundreds all working together, right?
Exactly. And you might think, well, more cores, more power, what's the big deal? But it's not always that simple. It's like having a team of chefs in a kitchen. More chefs can potentially prepare more dishes simultaneously, but only if the kitchen is set up efficiently. If they're constantly bumping into each other or waiting for ingredients, the extra help won't make much of a difference.
So it's not just about raw processing power, it's about making sure the entire system can keep up.
Precisely. And that's where the techniques from this paper, from DDFS, really shine. By drastically reducing disk access, they make sure the storage system isn't holding back those powerful multi-core processors. It's like giving those chefs a spacious, well-organized kitchen with all the ingredients they need readily available.
So DDFS isn't just about solving current storage limitations. It's about preparing for the future, where we'll be dealing with even larger amounts of data and even more powerful processors.
Exactly. And that brings us back to those other applications I mentioned. The cool thing is that the techniques we've been talking about, the summary vector, SISL, and locality preserved caching, they're incredibly adaptable.
I mean, they can be used for more than just data backups?
Absolutely. They have the potential to be applied in all sorts of areas where finding duplicates quickly is critical.
Like what? Give me some examples.
Well, take image recognition, for example. Imagine you've got a massive database of images, and you need to find near duplicates or quickly identify specific features. These techniques could be incredibly useful there.
So instead of manually comparing thousands of images, these techniques could help automate and speed up that process.
Exactly. And it doesn't stop there. Think about DNA analysis. Researchers are constantly comparing huge amounts of genetic data to find similarities and identify potential mutations. These techniques could make that process way faster and more efficient.
Wow, it's amazing to think about the potential impact these techniques could have in fields like scientific research, medical advancements, and even things like facial recognition technology.
Right. And while those applications might seem pretty far removed from data backups, the core principle is the same: efficiently identifying duplicates within massive data sets.
It just shows you how powerful these ideas can be when you start thinking outside the box. It's like we've stumbled upon a master key that can unlock all sorts of doors.
And that's what makes exploring these research papers so fascinating. We uncover the seeds of innovation, and who knows where they might lead us in the future.
Well said. But before we get too carried away, let's take a step back and recap what we've learned about DDFS and its secrets to speed.
Okay, great idea. So we started by discussing the challenges of traditional data backups with those clunky tape systems. Remember those? Then we dove into the world of DDFS, which uses data deduplication to slash storage needs and boost speed.
And along the way, we discovered the 3 secret weapons of DDFS: the summary vector, SISL, and locality preserved caching. Those are some serious tongue twisters.
I know, right? But they're worth remembering because they're what make DDFS so incredibly efficient. They work together to drastically reduce the number of times the system has to access the disk, which is the key to achieving those super fast backup and restore times. And remember, we're talking about a 99% reduction in disk access. That's huge.
Almost like magic, but it's really just clever engineering and a deep understanding of how data storage works.
And the best part is, these techniques have the potential to be applied far beyond just data backups. We've only scratched the surface of what's possible.
It's like we've opened a Pandora's box of innovation. Who knows what amazing applications are waiting to be discovered? So to recap, DDFS breaks those files down into variable length segments,
Right.
creates a unique fingerprint for each one,
Like a digital fingerprint.
and then only stores one copy
Yeah.
of each unique segment, no matter how many times it appears.
Exactly. Saves a ton of space.
And then on top of that, it's got those 3 secret weapons that make it lightning fast.
Yeah, the summary vector, SIL,
Screen-informed segment layout.
and locality preserved caching all working together to keep those disk accesses way down.
And the results are pretty incredible.
Oh yeah, 99% reduction in disk access.
Meaning backups and restores happens so much faster.
Blazing fast.
And we've even touched on how these techniques could be used for things like image recognition and DNA analysis.
Which is super exciting.
It really is. It feels like we've stumbled onto something really powerful here.
Absolutely, like a whole new way of thinking about data.
So as we wrap up this deep dive, what's the one thing you want our listeners to walk away with?
I think it's the importance of efficiency. As we generate and process more and more data, finding ways to store and retrieve it quickly and efficiently becomes critical.
It's not just about saving space anymore.
Right. It's about making the most of our resources, enabling faster analysis, faster insights.
And these techniques, they offer a really powerful blueprint for doing just that.
They're like essential tools for anyone working with large data sets.
Well, this has been a fantastic journey. We've gone from those clunky old tape backups to the elegance of DDFS, learned about its 3 secret weapons for speed, and even explored how these ideas could be applied in other fields.
Yeah, it really shows you how a deep dive into one area can open up a whole universe of possibilities.
Absolutely. And for anyone who wants to go even deeper, I highly recommend checking out the full research paper. We'll include a link in the show notes.
Yeah, it's a great read, even if you're not a tech expert.
But even if you don't dive into all the technical details, you now have a really solid understanding of how data deduplication works and why it matters.
And who knows, maybe this deep dive has sparked an idea for you.
Maybe you'll be the one to discover the next groundbreaking application of these techniques.
That would be awesome. So to all our listeners out there, stay curious, keep exploring, and keep those innovative minds working.
Couldn't have said it better myself. Until next time, happy deep diving, everyone.